Hello, everybody, and welcome to Chapter 9, Linear and Quadratic Inequalities. So this chapter uses some concepts that you did learn about in MFP 10, but it will also expand into examining quadratic inequalities. In the past, you had just studied linear. So section 9.1 is a bit of a review of some concepts from MFP 10, just to refresh our memories before we get into the quadratic inequalities in the next two sections. So first, we're going to recall graphing inequalities in one variable, but eventually we'll be going in two variables, which basically means on an XY grid, with X and Y being the two variables. But first, the most simple way to look at an inequality is if you only have one variable involved. So for example, if you are given the inequality X is less than 2, and an inequality, by the way, is a mathematical statement that involves a less than, a greater than, or less than or equal to, or greater than or equal to symbols. So it's an inequality because there's no equal sign, so we're not calling it an equation, we're calling it an inequality. So this is an inequality because we have the less than sign. So if X is less than 2, I'm going to mark 2 on my number line. Now it doesn't say that X can be equal to 2, so I'm going to put a hollow dot on the 2, and any of my solutions have to be to the left of 2. And usually we shade this in a little bit thicker on the line to show that that's the direction of the inequality. So the shaded region indicates where my solutions are. So for example, if I pick anything out of the shaded region, like 0 would be to the left of 2, and I plug it in here, 0 is less than 2 gives me a true statement. So anything that's shaded is a solution. Anything that's not shaded is not a solution. For example, 2 is not shaded. 2, if I substitute it in for X, is not less than 2. That doesn't make sense. So that's why we have to have a hollow dot on the 2. Okay, let's try the next one. So here, -3 is our important number. And we're saying that the solutions or the X values are all going to be less than or equal to -3. So this time, -3 is a possible solution. And so I'm going to shade that. And then I'm going to just try doing this a little bit smarter. Whoa. And making my pen thicker here to show the shading instead of trying to do it with a thin pen. Okay, so that's what that one would look like. So inequalities have often infinite solutions. And so we can't write what the solutions are. We often have to graph them or state them like so. Okay, this one's interesting. This one is telling us about a few things. So it's saying that -2 is less than X, which is less than or equal to 1. Because all of our signs here are pointing the same way, they're all less than signs or versions of less than signs, then we know that our lower boundary is -2 and our upper boundary is 1. We've seen this kind of notation when we talked about piecewise functions in previous units, so it's not completely new to us. The -2 is not included because it doesn't have that little bar underneath, so it's just a less than symbol, and the +1 is included. And anything in between would also be a solution here. So that's how we could show our solutions for this section graphically. Okay, so that was one dimension. Now let's take a look at when we have two dimensions. So we know that the graph of a line usually follows the pattern y equals mx plus b form. In this case, the m is 2 or 2/1, if it helps you to see the rise and the run there, and the b value is +1. So I know that my y-intercept is +1. So I can plot that on my grid. Now I can go ahead and use my slope to find a few more points. So up 2/1, up 2/1, up 2/1, and so on and so forth. So these points would create my line, but it's actually asking me to graph this, which is the inequality y is greater than or equal to 2x plus 1. Okay, so we need to know basically which set of x and y coordinates, or which set of points, is it the set on this side of our line or this side of our line, is going to make this true. So we are going to use a test point. So this line divides the Cartesian plane or the graph into two regions, the above region and the below region, which is on the right. One thing that I have to note is whether I'm going to connect these dots using a dashed or a solid line. And hopefully you remember this from MFP 10, but if we have that equals to little bar underneath, it's going to be a solid line because any of the points on the line are solutions. So I'm going to go ahead and graph that line using a solid. I'm going to change the color so it stands out a bit more. Using a solid line. Okay. So the question is my solution region over here or over here? So what I need to do is choose a test point, which is a point that's not on the line, and find out if it gives me a true or false statement when I plug the X and Y coordinates into this. So I'm going to try to pick a test point that's convenient for me to plug in. And the best, easiest test point possible is right here, 0, 0. If I can choose 0, 0, in other words, if 0, 0 is not on my line, it's always the easiest to use because everyone loves calculating the zeros. Okay, so I'm going to choose as my test point 0, 0. And I would say to choose 0, 0 every time unless it's on the line, in which case you'd have to choose something else. So what that means is, remember, this is my X and my Y coordinate. I'm going to put the Y coordinate in for the Y and the X coordinate in for the X. So I'm going to take my inequality and I'm going to substitute in my 0, 0 and see what I get. On the left side, I have 0. On the right side, 2 times 0 is 0, so I'm just left with 1. Now, is it true that 0 is greater than or equal to 1, or is it false? So this is false. This is not true, which means therefore 0, 0 is not part of the solution region, which means I will not be shading the side with this red dot with 0, 0 on it. In fact, I shouldn't even have anything marked there just to show that that's not part of the solution. And the part that I should be shading, I'm going to use my highlighter to shade. And I'm going to use green here. So my shaded region is this part over here. It's the other side. That means it must be the other side of the line. That's the shaded region. So as neatly as you can, try to show that. Some people just shade it with their pencil. That's fine. Some people, if they don't have a pencil that's good for shading, they'll kind of draw lines or something to indicate that this is the shaded side or the solution side. That also works. Just on the smart board here, I'm going to try and actually shade it. Okay, so all of the points in the green region are solutions. That means I should be able to pick out any point, plug it in, and it would give me a true value. Anything on this side, not part of the solution region. This is a mistake here. This part that's a little bit overlapped. Ooh, doesn't let me erase it, but try to be careful about that. So please note there are infinite solutions to a linear inequality. Solving a linear inequality means finding the solution region rather than just a specific point or points. So here's another example. Graph this linear inequality. And remember that our lines can be graphed using slope or using intercepts, whatever's convenient. On this one, I'm going to use intercepts just because it's easy. So to find the y-intercept, I'm going to set x equal to 0. Just to show you a different way to graph. So that would be 3 times 0 plus 2y is less than 6. Well, I'm getting 2y. Well, you're kind of using the equal sign version for now. We're kind of pretending that's our equation just to get the line drawn. And I'm going to divide each side by 2. So I get a y-intercept of 3. So I know that's one of the points on my line. So I'm going to find now the x-intercept. And once I have that, I'm ready to graph my line. 2 points is enough information to graph a line. So this time I have 3x plus 2 times 0 is less than 6. So 3y is less than 6. Actually, I was just using equals. So y is equal to 2. So there's my other point. Now I have to note on this one that it's going to be a dashed line because I don't have that little equal to bar on there. So the points on my line are not actually part of my solution region. So here's my dashed version of the line. So this is very important that you keep it dashed. Okay, and obviously you guys would hopefully have a ruler or something to kind of help with that. There is my line. I am going to put arrows on this dashed line here. So the fact that it's dashed means that the points on the line are not solutions. I'm going to test 0, 0 in my inequality. So I would end up with 3 times 0 plus 2 times 0 is less than 6. I get 0 is less than 6. That is true. That means 0, 0 is part of my solution region. So I'm going to shade that side. Okay, so that is what my final answer would look like. Here's a few more. This one I don't want to graph using intercepts because the 5 and the 4 don't go into 8. The 4 does, but the 5 doesn't. So I'm going to put it into y equals mx plus b form instead. So I'm going to move the 5x over. So I get a negative 5x plus 8. Now I'm going to divide each side by negative 4. Now, remember, when you multiply or divide each side by a negative, you must switch the inequality sign. So that should be something we should be remembering from Math 9 as well as MFP 10. So I now have a y, and instead of saying greater than or equal to, I have to say less than or equal to 5 quarters x, and then 8 divided by negative 4 is negative 2. So my y-intercept is negative 2. On this graph, I'm going to go up 5, 1, 2, 3, 4, 5, and over 4, 1, 2, 3, 4. There's another point. My next one would be off the grid. I'm going to work it backward just to get another point. 1, 2, 3, 4. So there's another one. Is my line going to be solid or dashed? It's going to be solid because I have that equal to bar underneath my less than sign. So I'm going to draw a solid line. Oh, it was still on dashed. Let's try that again. There we go. So I've got my solid line. Thank goodness it didn't go through 0, 0. So I'm going to test 0, 0 here. So I can already see the left-hand side is going to end up being 0, but in the interest of showing my work and communicating clearly, I'm going to show that step. So 0 minus 0 is 0. Is it true that 0 is greater than or equal to 8? This is false or not true. So therefore, I'm not going to shade the side with 0, 0. It's the other side that's going to get shaded. So there is my solution region. Of course, it goes on and on past where the grid ends. It's an infinite area here. Okay. Sorry, I couldn't. It's really hard for me to get that close, but hopefully that makes sense. I'm really trying to go right up to the line, but not over the line. Oh, man. Okay, moving on. Here is another example to look at. So I'm going to use intercepts this time because I can see that the 12 is divisible by 3 and 6. So I'm going to find the x-intercept, and that would be 3x minus 6 times 0 is less than 12. In other words, 3x is less than 12. or actually if I'm finding intercepts, I usually just use the equal sign. So x is 4. I'm going to find the y-intercept. So that would be 0 minus 6y is equal to 12. So y is equal to -2. Okay, is this line going to be solid or dashed? Looking at this, it's going to be dashed. So there's my line. Putting arrows on it and testing a point. So I can test 0, 0. So 3 times 0 minus 6 times 0 is less than 12. So 0 is less than 12. That's true. So therefore 0, 0 is part of my solution region. So this is part of the answer. So I'm going to shade this side. Oh my gosh, the coloring part is taking me a while here. Sorry about that. Okay, so there's our solution region. Okay, example 2, we're going to switch gears a little bit here and write and solve a linear inequality. So this time the equation or inequality is not necessarily given. It might be a word problem, and we're going to come up with it. So a sports equipment manufacturer makes footballs and soccer balls. One football requires 4 minutes on the cutting machine, and one soccer ball requires only 3 minutes on the machine. Determine an inequality that would represent the situation, and then draw its graph, and to show the number of each type of ball that could be made in 30 minutes or less. Okay, so we have to decide which variable to assign to which ball, and it doesn't matter which one you pick, but I am going to go with footballs for X, I think just because it listed it first. So X is going to be the number of footballs, and Y is going to be the number of soccer balls. So if you decide to switch that around, your graph would be similar to mine, but your X and Y values would be switched around. So it'd be a slightly different version of it. Now we're going to write the inequality, and remember that the time cannot exceed 30 minutes. So that's really important. That is a limit. Okay, and when we have a limit, that's when we're using our inequalities. So it tells us that it's 4 minutes for a football. So it would be 4 minutes times the number of footballs plus 3 minutes times the number of soccer balls has to be less than or equal to 30 minutes because we cannot exceed 30 minutes. So that's where this part comes in. Let's go ahead and change that into y equals mx plus b form. So I'm going to move the 4x over to the right side. I'm going to divide everything by 3, and I end up with y is less than or equal to -4/3 x plus 10. Don't forget the 30 gets divided by 3 as well. I did not have to change the direction of my sign because I divided by a positive. So that was able to be maintained. I'm just going to label along here to what I defined. So I'm going to reiterate that my x-axis is the number of footballs and the y-axis is the number of soccer balls. Okay, so I'm going to go ahead and graph some of my information. So my y-intercept is 10. From there I go down 4, 1, 2, 3, 4, and over 3, down 4 and over 3. And is this line going to be solid or dashed? It's going to be solid. Okay, so there is my, oh, missed hang. Forgot to change the most important thing. It's supposed to be solid. Here, let's try that again. Okay, so I'm going to continue this. Now I'm feeling a little bit lost here. Where exactly is this going to hit? But I'm following my points as best I can. And I'm not going to draw my line going on forever this time because it doesn't make sense to be making a negative number of soccer balls or a negative number of footballs. So I'm going to stop myself when I hit that x-axis. So this is a situational problem where you don't necessarily put the arrows on and go on forever. Word problems, you really have to pay attention. Okay, so now we're going to check our point. of 0, 0. And I'm going to check that in my original up here. I find that the easiest one to use to check. So 4 times 0 plus 3 times 0, is that less than or equal to 30? And I get 0 is less than or equal to 30. Now, one other thing to consider, and to be honest, I can't remember if your textbook goes into this style or not, but I'm going to reiterate it, is that we will only have discrete solutions only. I'm going to assume that we cannot make part of a soccer ball or part of a football. It didn't really say in the question that that was the case, but I'm going to assume it. So can only have whole numbers of footballs and soccer balls. One time you know that it's, or one situation where you know it's definitely discrete is when you're talking about people. Like you wouldn't have 2.2 kids. You either have 2 kids or you have 3 kids. So I'm going to, instead of shading this region, I'm going to thicken my pen a little bit just so you can really see where I'm drawing these dots. And I'm going to dot every spot that includes whole numbers of my X and Y values. I think it goes right through that point. This one would be included. So technically, these are my solutions. And so that's why I'm not shading. So you'll sometimes see the dotted region and you'll sometimes see a shaded region. Now what that means is I should be able to select any of these points and it should make sense. So for example, this point is 2, 6, which means I could make 2 footballs and 6 soccer balls in less than 30 minutes. Okay, I could make 3 footballs and 6 soccer balls in less than 30 minutes. I can make 0 soccer balls and 0 footballs in less than 30 minutes. So those ones all make sense. Anything on the line works, but anything past the line does not. So I'm not shading this point because it's to the right of the line. And to be honest, I can't remember if your textbook does that or not. If it just shades it, then that would imply that everything's possible, including partial footballs and soccer balls. But if you see the dotted region, it's because we have discrete solutions, which means no partial values. Okay, so these aren't continuous. Things like time or growth of something are often continuous. Things that are about items are usually discrete. Okay, let's take a look at another example here. So Barb has started a new fitness program. She knows she can burn 500 calories per hour jogging and 300 calories per hour walking her dog. Barb wants to do a combination of the two activities and burn at least 3,000 calories a week. Draw a graph to show the possible workout combinations she could do in a week. Select one possible combination and check it in the original inequality. Okay, so we're going to start by assigning our X and Y values here. So we're going to let X equal the number of hours jogging. And we're going to let Y equal the number of hours walking. So those are our 2 variables. And we'll come up with an equation here of how many calories she'd be burning. So, I'm on my highlighter. So by jogging, she burns 500 calories. So 500 times X, the number of hours jogging, plus 300 times Y is going to be greater than or equal to 3,000. She's okay with being greater than 3,000. She doesn't want to be less than 3,000, so at least 3,000 calories. Okay, we're going to rearrange this now into Y equals mx plus b form. So I'm going to move the X value over to the right. And I'm going to divide each side by 300, which actually will help our numbers become more manageable. So the zeros will cancel. So I get negative 5/3 X and 2 zeros will cancel here. So I get plus 10. So there is my inequality. So I'm going to go ahead now and graph that. So Y was number of hours walking. and X was number of hours jogging. And again, are we going to have negative values? No, we're not going to say somebody walked -2 hours. That doesn't make sense. So there should be nothing in these quadrants. Everything should be here in the quadrant where our X and Y values are both positive. So I know that I have a y-intercept of 10. From there, I'm going to go down 5/3, down 5/3. You don't need to relabel these. We assume they're ones all the way unless shown. If you want to label the numbers along the bottom, you can. This is going to be a solid line. And I am not going to go past the x-axis. So there's my solid line. Now, I need to choose a test point and go from there. And I also need to, sorry, I'm just looking at my answer key. And no, that was correct. Okay, perfect. And I also need to decide if this is a discrete or continuous case. When you think about burning calories or spending time jogging or walking, those are actually continuous activities. You can't get from 1 minute to the next minute without hitting every single second and millisecond in between. And the same thing with burning calories. You don't just suddenly burn 5 and suddenly jump to burning 10. You have to burn them all the way in between. And so we actually will shade this one instead of dotting it. The question is, which direction am I going to go? So I'm going to use my test point of 0, 0 to see if that works. So if I put that in, does it give me a true or false statement? I end up with 0 is greater than or equal to 3,000, which is false. So I'm going to shade outside of the line this time, or to the right of the line. Okay, so there is the solution for Barb walking. I probably should label the graph. I don't remember if I did that last time, but that should be what I'm doing. So this is Barb's fitness program. All right, let's take a look at an airplane. Okay, so an airplane can hold up to 1,500 kilograms of luggage. Economy class passengers are allowed to bring 15 kilograms of luggage. First class passengers are allowed to bring 45. Assuming that each passenger brings luggage at a maximum allowable weight, draw a graph showing the possible combinations of allowable luggage weights. Select one possible solution and check it. Okay, so we're going to assign our x and y variables. This time I'm going to let x equal the number of first class passengers. And let y equal the number of economy passengers. Okay, and then we're going to write our equation for total weight here. So it would be 45x plus 15y is less than or equal to 1,500. So we can hold up to 1,500. And everything was in kilograms, so we're good to go. I'm going to arrange that in y equals mx plus b form. Divide each side by 15. Okay, so this time it's a little bit more awkward because I've got to go all the way up to 100. So I have to rescale this and say that instead of this being a 10, this is going to be 100, which means every square is worth 10 instead of being worth 1. So I'm going to indicate that all the way up. And this was the number of economy passengers. And this is the number of first class passengers. I'm not going to have negative numbers of passengers, so everything's going to be up here in quadrant 1. And from here, along this scale, as long as I keep my scales the same, so I'm going to do the same thing, but actually I'm just going to label every 2. So 20, 40, 60, 80, and then 100. Okay, and my slope is -3/1. And because I've scaled these the same, I can just count squares. So 1, 2, 3 down and 1 over, 1, 2, 3 down and 1 over. So that's the advantage of scaling these identically. Then my slope makes sense to just count it as on the squares on the grid. Now, would this be a solid or dotted line? It's going to be solid. So let's go ahead and draw that. Good, I am solid. Okay, so going all the way down to here. Now, I guess the question is luggage continuous or discrete? And I'm going to say it's discrete. It comes in separate bags. So we're talking about we're not talking about luggage, we're talking about passengers. Passengers definitely discrete. So we're going to dot our final answers instead of shading. Make it a little bit thicker. Yeah, that's the one. And so I could have 0 and 0 passengers. I don't see why not. And I'm going to symbolically dot these, even though I know they're going up by tens. It's just a way of kind of symbolically showing that our answers are discrete. I need to test one of those just to mix it up. I'm not going to test 0, 0. I'm going to show you what it looks like to test something else. So I'm going to test 2020. Just for interest's sake. So 45 times 20 plus 15 times 20 is going to be less than or equal to 1,500. So that's 900 plus 300 is less than or equal to 1,500. So I got 1,200 was less than or equal to 1,500, which is true. So that's why I knew we were going to be shading this way. Also, knowing that this was the upper limit, not the lower limit, helps me to understand that the shading is going to take place within that triangle. Okay, example 3, let's take a look at how to write an inequality if we're given the graph. So first we have to find the equation of the boundary line. So here's our boundary line. Well, we know that the form of this line is going to be y equals mx plus b. So I have to find the b value, which is 5. And the slope is -1 and over 1. So our equation is y equals -x plus 5. So we have to decide. We have to have a test point and decide what's happening. So I'm going to test something that's part of the solution region. And that will actually give us what direction our inequality faces. Is it going to be a less than or an equals to? So when we don't know that, we use a test point from the solution region. So something from the shaded area. So luckily 0, 0 is available. So I'm going to test 0, 0. So it looks a little bit different now. What it's going to tell me is that 0 is actually, instead of putting an equal sign, I should actually have like a question mark. I don't know what's going to go there. No such thing as -0, so that just becomes 5. The question is 0 less than 5 or greater than 5? So if I fill in that question box, I know that 0 is less than 5. Because it's a solid line, I know I have to have the bar, and that's because it's solid. So my final answer is going to be y is less than or equal to -x plus 5. Let's take a look at another one. This one's dashed. Okay, just making a few notes. My y-intercept is 1. My slope is 2 over 1. So y is equal to 2x plus 1 would be my equation of the line, but I need to test something. I can't test 0, 0 this time because it's not in my solution region. So to me, the easiest point would be maybe -1, 1. So I'm going to put those values in to my equation and come up with the right symbol. So I end up with 0 on the left and -1 on the right, and 0 is greater than -1. It was a dashed line, so I'm not going to put a bar underneath that. So my final inequality is y is less than, pardon me, facing the wrong way, I lied, I have a greater than sign. So it's going to be y is greater than 2x plus 1. Here we go, on to C. The b value is 5. The slope is -1, 2, 3 over 2. So our equation that we're thinking about for the boundary line is -3 over 2x plus 5. So that's what we're thinking about. I'm going to choose a test point. Can't choose 0, 0. It's not a solution. So I'm going to choose 10, 10. Why not? I know it's eventually going to be shaded, and those are nice, easy numbers to work with. So 10 divided by 2 is 5. 5 times -3 is -15. So I get 10 and -10. And so 10 is greater than -10, and it's a solid line, so I'm going to put the equal sign on there. So it's greater than or equal to for this inequality. You could go into Desmos and check your answers by plugging this in exactly as you see it. Okay, so here we're going to use what we've learned in Chapter 8 about solving systems of equations graphically to hypothesize what solving a system of inequalities might involve. So when we did Chapter 6, we were graphing lines or lines and parabolas and finding intersection points. Now that we're working with inequalities, we're going to look for intersections of regions, entire regions, not necessarily just entire points. So this is a really great example to take a look at. Okay, so here are our two inequalities. We're going to graph each of them, and then we're going to graph their solution regions, and we're going to see where they overlap. And that will be our ultimate solution region for this question. So my first one, I'll do it in blue. And so I get y is greater than or equal to 2x plus 6. So here's my plus 6 part. The 2x means I'm going up 2 and over 1 to get to my next point, like so on and so forth. I'm going to go backward as well, just to pattern this as far back as I can to get an accurate picture of this line. So I've got quite a few points. It's going to be a solid line because it's got that bar on it. In fact, they're both going to be solid, just making a note of that now. And here is my first line. I should now label this line because I'm going to have more than one line on here. So this is the line representing y is greater than or equal to 2x plus 6. I'm going to shade this in blue highlighter just to show what this solution region is. Okay, if you're doing this by hand, you can just shade it lightly, or again, you can make some stripes in a direction that makes sense to you, and then maybe in the next one you would stripe it in the opposite direction. Okay, so let's scroll up here. Take a look at our next line. It's got a y-intercept of 2 and a slope of -1 over 2. I'm going to do that one in yellow would be my preference, but it's really hard to see, so I'm just going to do it in red. So the y-intercept was 2, and the slope was -1 over 2. So as best I can, and again, this one was going to be solid, but I'm going to change it to red. So this is y equals -1/2 x plus 2. So there are my two lines. Now this solution region, oh, I never showed my test point up here. Sorry. I was just looking at my answer key. Back it up to the blue one for a second. The blue one, if I tested on the blue one 0, 0, I would get 0 is less than or equal to 2 times 0 plus 6. So 0 is greater than or equal to 6. So 0, 0 is not part of my answer region, hence why I shaded the blue line to the left. Okay, I'm going to show that a bit better here. So I'm going to test 0, 0. So 0 is less than or equal to -1/2 times 0 plus 2. So 0 is less than or equal to 2. So that's true. So I am going to shade in the direction of 0, 0, which means I'm going to shade under the red line. I'm going to shade it in yellow for a specific reason with my highlighters. So it's going to do something interesting. So here is my solution region. And when I overlap, you can see that it changes it to green because the yellow overlapping with the blue is the green. So hence why I chose these colors, just because it happens to show it nicely on the smartboard. But I will show you in pen over top a way that you can show it if you don't like shading. It's kind of a quick way you could show it as well. So it's quite obvious to me where these overlap is this region. And in fact, all of this stuff overlaps too. So anything in this section and further to the left and further down. Okay, so if you don't have highlighters or something like that, or you're doing it in pencil, which most people are doing, when you show your solution regions, if you can't shade them that nicely, you could do the blue one, say going this direction, and you could do the red one going this direction. And I think it's fairly obvious where your solution region is. That's where your hatch marks go cross hatch, or they overlap, make like a basket pattern. Okay, that takes us to the end of 9.1. Okay, so thanks for tuning in for that. Hopefully it's mostly a review of stuff that you maybe knew already from MFP 10. But once again, if you have any questions, please let me know. Otherwise, thanks for tuning in and have a great day, everybody.